Hi everyone, thanks for coming today. My name is Adi Andrei, and for the best part of the last 20 years, I've been involved in essential roles with R&D projects for organizations like NASA, Unilever, Philips, British Gas, and quite a few others. And tonight, I'm going to talk to you about finding atypical patterns in large data sets, and most specifically in airline data and time series. I just put this outline so that if the talk gets boring at any time, you know kind of where you are. I'm just going to talk a little bit about atypicalities, what they are and why they're important. And then I'm just going to present to you a real-world application where atypicality detection was very important. It was quite successful, and it was done with a very interesting technology, which I believe is still state-of-the-art today. First, to get into this topic, there's a big difference, I'm sure everyone knows, between patterns and values. So atypicalities refer to patterns. We're looking for unusual or out of the ordinary patterns versus a value. So if you look at this, can you tell me what's the, or where are the, from 1 to 7, where's the unusual values?
5, 3, 5.
Okay, who's for 3? Okay, who's for 5? Okay. So overall, you're wrong. So 3 is atypical values, but the pattern is the same as almost everything else. So 5 is the unusual pattern because it does this thing. 3, the pattern is the same, it's just the value that is different. Which one do you think it's easier to detect by computers? 3 or 5?
3.
Okay. So you already see what the challenges start to become when you're trying to find atypical patterns. Why atypicalities? Most of data science, with the exception of the things that Carlos just showed you before, try to deal with what's the most frequent, more regular patterns in your data. Atypicality detection takes this a little bit one step farther, and it's about, there may be a lot of patterns in your data. Which ones are the ones that are really important to look at? Because you might not have the resources to look at all of them. I mean, we're talking big data. So, and in practice, they're relevant because in mission-critical operations, things that are out of the ordinary, that are unusual, can signify that there's a latent problem that's developing in the system that later might result in large loss, including loss of life or everything. So discovering these atypicalities early on, it's very important in mission-critical systems. So that's about it. Are you guys with me so far? Does it make sense? Why we do atypicalities and not regular patterns? Okay. Aviation, as you all know, it's typically one of the safest means of transportation. Everything on an aircraft is certified, including the latest bolt. It has to come with its certification. There are very strict rules and procedures for all operations, and the safety is continuously monitored because, one accident can create a lot of trouble. And they know that when flights operate outside the norm, there could be safety issues. And traditionally, the safety analysts, the airlines, they do have tools that monitor safety by comparing the data that comes from the flight recorders and so on with preset parameters in order to identify what they call special events, which is atypical events, things that should not be happening. Like if you are at a certain or below a certain speed and your flaps are off, that's a problem, and so on. So, but the question is, what happens with things that you didn't expect them to happen, or you didn't even know to look for, completely unforeseen issues? So in 1999, the US Congress gives NASA a mandate, and it says, make aviation safer by developing advanced tools that can find latent safety issues in these large data sets that you've been collecting. The airlines have been collecting large amounts of data way ahead of all the other industries, especially through their flight recorders. The basic workflow, it's pretty simple. The plane arrives at the airport, the flight recorder is taken out, the data is downloaded into a big database, processed, then mission control or the airline personnel looks at the different reports, and then they have to analyze and validate the different information that's being presented to them. And then whatever they learn and the feedback is being incorporated back into the system. So, I hope you're all buckled up, because now we're going into technical details. What kind of data are we talking about? There's about 10,000, about 1,000 sensors on an airplane that record everything every second, sometimes 4 times a second. And you have about 9,000 seconds on average flight duration. This is US data. And 30,000 commercial flights per day, which it's about 270 billion data points per day that you need to process. The challenge is that how can we find potentially interesting issues in this large amount of data? And how can we do this fast and reliable given the technology constraints at the time? On the left there, you have the workstation that I've been working on this project from 2001 to 2005. It's a Dell Inspiron with a 1 Pentium 3 processor, 900 megahertz, the speed of the processor, and half a gig of RAM. By comparison today, the average mobile phone specs in your pocket right now would be probably better than this. This is a 2012 Galaxy S3 that has a quad-core processor. It has 1.4 gigahertz speed and twice as much RAM than the workstation that I was using when doing this thing. The methodology, this is just a quick list. So we would have to separate flights, to separate the data by flight phases. We're going to create a feature matrix. Then we're going to have to do a series dimensionality reduction, compute atypicality, create a plain English text that explains why something is atypical, and also offer a visualization that explains why the thing is atypical. The reason we have to split by phases is because we don't want to compare apples with oranges. So I don't want to compare things that what happens at takeoff with what happens at arrival or landing. So we want to compare takeoff data with takeoff data, and usually at the same airport. So if I compare takeoffs at Heathrow only with takeoffs at Heathrow, I'm not going to compare them with LAX or something else. And also the same type of aircraft and so on. So splitting by phase gives a good separation in the data that then the typicalities we find are more relevant. This is what the raw data looks like. And this is just, I don't know, like 10 out of the 1,000 parameters. Eventually, we reduced everything to 135 parameters that our domain experts, which were retired pilots working for NASA, told us those would be the only significant ones to look at. So that was the first data reduction. And almost all of them are time series that look like that. And this is where we're looking for atypicalities. So the first thing is, okay, feature extraction. How do I transform that time series into a vector of numbers such that the properties of this curve are being captured by this fixed vector of numbers in such a way that it would allow me to compare this curve against other curves, other time series, similar time series coming from other flights in order to detect if this was atypical or not. And in order to do this, if you have any questions at any time, please interrupt me. This is technical stuff. When you look at it the first time, might not come very easy. So what we did when you have the whole phase, we take a sliding window. This is a technology slightly borrowed the methodology from digital signal processing. So we take a sliding window, in this case an 11-second sliding window, and then we do a quadratic fit, or a polynomial regression of the second order, whatever you want to call it. What this quadratic fit does, it gives us the coefficients, the A, B, and C for this curve that it's the best approximation for those points. So for these 11 seconds, we have 3 numbers that actually are pretty good at depicting the qualities of the data for that portion. We take a 4th value, which is basically the error or the noise, the sum square of error divided by the degrees of freedom, and squared. So this gives us a 4th parameter. I don't know if anybody can see here. So the A, it's representative of the average value. B is representative of the speed of change of the value. C, or curvature, is the acceleration, the speed of change, and D basically is the noise. So we get this for a window of 11 seconds, and then we slide this window across the whole phase. And we get the ABCDs for every window in the phase. Yes.
Why it's 11 seconds?
It could be anything. It's just based on our research that seemed to be the best in order to capture what's happening. Because if you have major things happening, you want it's like almost like a resolution, like when you do digital to analog to digital conversion. What's the best thing so that you don't lose information? What's the best quantum to take? So 11 seconds have to be the best. Yes. Okay. And then what do? We aggregate these ABCDs across all windows, and we take the minimum, maximum, average, and standard deviations. So we end up with, you see here, the feature vector, which has 4 values for each coefficient, which we believe expresses the time series in a way that's good enough to be able to compare it against other time series and then be able to find atypicalities. Yes, go ahead.
How many seconds of it slide?
No, just every second.
Oh, just
yeah.
just
Yeah.
Yeah,
Yes.
I'm just wondering if these slides will be available.
Yes, they will.
We can't really see.
They will. Yeah.
Yeah.
All the slides will be available.
Okay, anybody else? Yes, please.
Yes, what if you select minimum maximum average distribution? Or other that you could use to then release the numbers for?
Well, they're easy. Well, they're not so difficult to calculate. Also, they tend to capture what's happening with that value pretty well.
Like the median, for example.
Yeah, we could have picked up the median.
So you could.
But this is like kind of like a real world situation where once you find what's good enough, then you kind of go with it. But yeah, I mean, there could be a whole study of what would be the best things to choose. But I think the increase in efficiency or in precision and so on would be minimal compared to these things, which are kind of the standard. So we got our feature vector. And then we do this for every parameter, because this is just for one time series and for one phase. So when we do that, we end up with our feature matrix. So for each flight, we have 16 values for each parameter, which ends up being about 2,000 different columns. We need to reduce this, so we apply the standard principal component analysis, which reduces this to less than 50, sometimes even to 10 components. So that's our final feature matrix, 50 components times number of flights. The number of flights usually is around 10,000. So we look at the last 10,000 flights at that airport. So even there we use this moving window because we don't want to compare necessarily with last year. We want to compare with what happened in the recent past. So that's why that baseline of 10,000 flights always keeps being updated. So now that we have our feature matrix, we need to see how do we compute if something is atypical or not. And you can think of flights as each flight being like a point in the space, in a 50 or less dimensional space. And we want to find which one of these points is really an outlier, really away from everything else. So we need to use a similarity matrix. You can intuitively think we could use Euclidean distance, but the problem is that the distribution is not uniform. So I can't use just Euclidean distance or like think of normal distribution and take how many standard deviations from the mean, because the distribution is not uniform. So then we have this thing which most people with background in statistics are familiar with. It's called the Mahalanobis distance. What Mahalanobis distance does, it takes into account the shape of the distribution in each dimension. So for example, if you look at the points A and B, A is much farther than B, much farther from the center of the distribution than B. So Euclidean distance would say A is atypical. But if you look at the shape of the distribution, actually A is more similar to the distribution than B. So that's what Mahalanobis distance does. Does that make sense? And then we want to get a value between 0 and 1. So over here on the bottom, if you can see, this is the Mahalanobis distance. We call it the typicality score. And then we have a distribution of it, and you can see it has like a gamma distribution, or the gamma distribution was the closest to how this looks like. Therefore, we calculate a p-value assuming the gamma distribution, and that gives us a value between 0 and 1 for atypicality. Now, there's something else we want to take into account. Things like this inlier or the outlier, they by themselves, they're definitely more atypical than the ones that are in a big cluster. So we want these outliers also to have their atypicality score increased. Therefore, we add this cluster score, which is the cluster size divided by the population size, again, a value between 0 and 1. And then we compute the global atypicality, which aggregates both scores using the p-value and the cluster score. And then we use the minus log so that most atypical flights will result with the largest global atypicality scores. And then when you look at what comes off here on the bottom, these things would be like really high. So we cut them here, but say like it's like it would go 10 times the size of the screen. So, and you end up with a few over here, which are the most atypical. Is that making sense? You with me? Yes.
Remind us what the p-value is of, what distribution is that?
The p-value is the probability that that element is part of that distribution. So the p-value being very low means this is very atypical. And then you take the minus log, so it reverses it, and it increases its score because it's very atypical.
I guess the thing that I was confused about is exactly what is the space, what is the distribution, what is the space of function clustering? Is it the sum of all of the ABCDs over all the windows?
No, the aggregate values across all windows, that gives you the feature vector. And then you have for all parameters, you have 16 values, and then you reduce that with principal component analysis. So each point is a flight that has 50 components.
Right.
So it's 50 dimensional.
It's the PCA, each feature.
Can we leave the question for the end, because
Right.
we're a bit tight on time.
Okay.
All the presentation.
You can come to me after, or
Very
so.
short.
Now that we have a global atypicality for each flight, the only thing we have left to do, well, one of the things we have left to do is to rank them based on this. So we just sort them, really, based on their atypicality. Now remember, the atypicality is computed in each phase, so then it has to be aggregated across all flights. And the top 1%, we put them in red, the top between 1 and 5% in green, and 5 to 10% in blue. And then the flights, same thing, except we use yellow instead of green. So you get the list here. This is the most atypical flight in red, and this is what happened in each one of those phases. This is taxi, takeoff, slow speed, fast speed ascent, low speed ascent, I think cruise, and then this is the landing phases. So you can see for each flight how atypical it was in what phase. Is that right? That's where we want to get at, really. So basically it says these are the flights are interesting to look at, and those are the phases and how atypical they were in those phases. Now we also want to know why, or an analyst might want to know why. So there's two things. There's the rationale and the performance envelope. The rationale is you can see it here. Average value is higher than normal during takeoff. It's focused on just one parameter at a time. How we compute it, we really go and see how many standard deviations that flight was from the perspective of just that parameter. And then the performance envelope is basically a heat map of all the instances of all the other flights that we compare this flight against. So you can see where it's more intense here. So most of the flights were around here for the fuel flow at takeoff. This guy just went way high and then down. And this is how it all comes together. This is the actual the analyst interface for the morning report. So you have the flights over there, you have the phases, you click on a phase, you get the most atypical parameters that generated that atypicality. And then you click on a parameter and you get its performance envelope and the rationale here. So for this one, the minimum value was lower than normal during low speed descent. You also get a lot more information over there about its own clusters and other special events detected and so on. And on the bottom you have the whole, what happened for the whole flight. And this is the phase that we're looking at here, just this one over here. So this is what the analyst had as their final user interface. So how did this thing go? It started finding atypicalities, and these are some of the atypicalities it found, the high energy arrivals. This is when the plane comes in, but it comes in too high. So the gliding path is a bit too high, and then they have to land with very high speed. And we know that this goes into unstable approaches, which can lead to accidents. So what NASA learned from this was, okay, we need to monitor the energy at approach. And they created a new parameter called the kinetic energy on approach, which then the pilot can be told exactly when that's going to fly, and in order to either abort the approach or do something else. As well as other anomalies that I don't have all the time to go through right now. This is just one atypicality. It's an atypical takeoff. It's also called a full power takeoff. So this guy just put the pedal to the metal and just took off. And that's what it looks like when you look at the data. You can see like the airspeed was way higher than everybody else. Here it started going high. Here was on top, and the fuel flow. So finally, NASA and Onera, which is the French equivalent of NASA, and Airbus and EasyJet did a study where they compared the morning report versus the current technologies that they're using. Well, this was in 2009, I think. Yeah, over there. And the conclusions of the report, in a nutshell, were that the morning report did reveal very interesting operational situations that could have not been identified otherwise. And also that the number of the atypical situations identified was small enough that it was practical for a safety officer to work with it, which was very important. So this is the end of my talk. The conclusion, finding atypicalities have been proven in a real world to identify relevant operational situations that could have not been identified in any other way. And this is just one way. I mean, we focused on flight data and time series, but this can be, unusual patterns can be found like in out-of-stock events, or I worked for sales data, boiler sensor data, and so on. So, yes?
Oh, sorry. So
I'm just wrapping it up, so I'll open it for questions. All right, so I think that's it. Thank you for.
Yes, I am curious about the use of principal component analysis in the context of anomaly detection, because principal components identify axes of maximal variation. And it may be that you have feature parameters that are normally incredibly stable, but once in a while you get for a small time window a spike. Now, given the principal component analysis, I don't think you would ever be able to detect an event.
Well, I mean, that's a very good question. So I didn't present everything. I mean, this is a five-year project. I mean, it was a 12-year project. I've been part of it for about 4.5. So that was one of the problems that came up. So what we had to do was to see, okay, for these parameters that all the time are constant, but sometimes they just have very small variation, which came up huge because, you know, it's like an infinite standard deviation. So we used the domain experts, the pilots, that would say, okay, for this thing to a meaningful variation has to be at least this much. So we had a whole table for each parameter, what is a meaningful variation, and if that wasn't there, it was excluded from the analysis.
Okay, we have another question. Maybe we go to Tom because we're a bit short of time. Any other question there? Yeah.
what technologies you've been using? Because you mentioned that it was massive amounts of data.
Can you repeat the question? For
Yeah,
the
so
audience?
what technology we've been using? Microsoft SQL Server on a dual processor, 4-core in total Dell server, circa 2005. It wasn't all those data points. It was 4 major airlines because we built a proof of concept, but we were doing this with 4 major airlines, which was American Airlines, Delta, Northwestern, and Alaska Airlines. So we had a pretty big amount, but yeah, that's what we were doing. Your mobile phone today, probably. But the point was, we tried to use as simple things as possible. We could have gone into wavelets and Fourier transforms, and there's been some analysis done on that, and it was not much better, or actually it was worse than using the simple minimum maximum standard deviation for a quadratic fit. So yeah, we actually having all these limitations made us to be very creative, but in being very creative also be very simple. So.
Okay, well, thanks.
Please come to me if you have any questions, anything.
You have any questions?
Visit the website.
You're going to be around
to share the information.
You're going to be around later.
I'm going to be here.
Well, thanks.